Have you ever looked at a simple data table like a spreadsheet and thought, yeah, this looks fine, only to discover later that it's basically a house of cards just waiting to fall over? Well, hidden inside what looks like organized data, there's often this potential for total chaos. Today, we're going to pull back the curtain and learn the step-by-step process for turning that chaos into clarity.
Okay, so let's just dive right in with a real-world example. Imagine a software company, and they're tracking all their projects. Seems straightforward enough, right? But as you're about to see, one poorly designed table can cause some major headaches. So take a look at this. At first glance, this table seems perfectly fine. We're tracking projects, we've got the project ID, the project name, and then we have all the employee details right there. Their ID, name, job title, and so on. It's all in one place. But here's the problem. Mashing all this info together has created a ticking time bomb of data problems. We call these anomalies.
So here's problem number one, the insertion anomaly. Let's say we just hired a new programmer. Awesome. We want to add them to our database. But we can't. Why? Because to add a row, we need a project ID, and they haven't been assigned to a project yet. We are literally blocked from entering perfectly valid information about a new hire, all because another piece of data is missing. The very structure of our table is getting in the way of doing business.
And then there's this mess, the update anomaly. So the client calls and says they want to rename the Manhattan project to, let's say, Project Apollo. Okay, simple enough. Except in this table, the name Manhattan appears in 4 different rows. That means you have to go in and manually change it in 4 separate places. And what happens if you miss one? Well, now your data is inconsistent. You've got the same project listed under 2 different names. That's a recipe for disaster.
And finally, we have the scariest one, the deletion anomaly. Let's imagine the Manhattan project gets canceled. So the logical thing to do is delete all the rows associated with it. We delete those 4 rows and poof, the project is gone. But wait, what else did we just do? We also accidentally erased all records of employees like Paulo Farias and Carlos Alberto. Their names, their job titles, their hourly rates, it's all gone. Our database just forced us to delete valuable employee information just to get rid of a project. That's a huge problem.
You see, these anomalies aren't just little annoyances. They are fundamental flaws, bugs, that are baked right into the structure of our data, and they are actively corrupting it. But thankfully, there's a formal, systematic process to design our way out of this mess, and it's called normalization.
Think of normalization as our cleanup strategy. It's a series of quality control stages, or tests, that we put our tables through. We call these stages normal forms. By taking our data through this process, we methodically hunt down and eliminate redundancy. And in doing so, we protect our data from all those dangerous anomalies we just talked about. So here's our game plan. We've seen the danger, and we know what normalization is. Now, we're going to walk through the first 3 stages, first, second, and third normal form, to see exactly how we transform this chaos into clean, reliable order.
Okay, let's get our hands dirty with step 1. This first stage is all about setting up the most basic, fundamental rules for organizing our data properly. The absolute core rule of first normal form, or 1NF, is something called atomicity. It's a fancy word, but it just means one single piece of information per cell. That's it. No lists, no comma-separated values, just single, indivisible nuggets of data. And on top of that, every single row in the table needs a unique identifier, which we call a primary key.
So here's our checklist for 1NF. First, make sure every column has a unique name. Second, make sure all the data is atomic, indivisible. Third, get rid of repeating columns, like phone 1, phone 2, phone 3. And finally, every single row gets a unique primary key.
And here is a textbook example of a 1NF violation. Look at that email field. It has 2 different email addresses stuffed into one cell, separated by a semicolon. This value is not atomic. You can easily break it down into 2 separate pieces of information. Now just imagine trying to write a program that sends an email to that person, or trying to search for one specific address. It becomes a total mess.
So how do we fix it? We break the table apart. It's a process called decomposition. We create a brand new table just for emails. Now each email gets its own row, its own unique ID, and we link it back to the customer using the customer's ID. Just like that, every single cell contains one and only one piece of info. Our data is now atomic, and we've officially reached first normal form.
All right, with our data now atomic and every row uniquely identified, we've passed the first test. So it's time to move on to the next level of organization, second normal form. This is where we tackle a more subtle kind of redundancy.
So the rule for 2NF sounds a little complicated, but the idea is simple. Every column in the table has to depend on the entire primary key, not just a part of it. This really only matters when we have what's called a composite key. That's a primary key made up of 2 or more columns combined. If a column only depends on one piece of that key, we've got a partial dependency, and that's the problem 2NF is designed to fix.
Let's go back to our project table. Imagine for a moment that the primary key is the combination of the project ID and the employee ID. Together, they make a unique row. Now ask yourself this: what does the employee's name depend on? Does an employee's name change depending on which project they're on? Of course not. Their name only depends on their employee ID. Because the name depends on only part of that composite key, we have a partial dependency. And to fix this, you guessed it, we split the table again. All the information that depends only on the employee ID, their name, their job title, it all gets moved into its own dedicated employee table. The only thing left in the middle table is the one piece of information that depends on both the project and the employee, the number of hours they worked on that specific project. And just like that, the partial dependency is gone. We're in 2NF.
We are so close. Our data is looking way cleaner, but there's just one more common type of redundancy we need to stamp out. This final step in our core process deals with an even more subtle kind of dependency. Okay, for a table to be in third normal form, or 3NF, it first has to be in 2NF. The new rule is this: no transitive dependencies. This happens when a column that isn't the primary key determines another column that also isn't the primary key. Think of it like a chain reaction. The primary key determines column A, and then column A determines column B. That indirect link is what we need to break.
Let's look at our new employee table. Take a look at the hourly rate. Now, is that rate really determined by the employee's unique ID? No, not directly. It's determined by their job title. All senior developers get the same rate, right? So we have this chain. The employee ID determines the job title, and the job title determines the hourly rate. That's a classic transitive dependency, and it's a problem.
So for our final split, we create a new job role table. This table simply stores the job title and its corresponding hourly rate. The employee table now just needs a small reference, a foreign key, to the job ID. And with that, we've done it. Every single column in every single table now depends only on its primary key, the whole key, and nothing but the key. This is third normal form. Okay, let's just step back for a second and look at the huge transformation that just happened. We started with what looked like a simple table, but it was actually a minefield of potential errors just waiting to happen. And this, right here, is the payoff. We traded one big, messy, unreliable table for 4 clean, efficient, and interconnected ones. We went from high redundancy and a huge risk of anomalies to a system where our data integrity is protected. We can now update a job's pay rate in one single spot and trust that it's correct everywhere. We've built an efficient, stable structure with a single source of truth for every piece of data.
In the end, normalization isn't just some academic exercise for database nerds. It's a fundamental skill for building reliable systems. It forces us to think clearly about how our data is actually related. And that leaves us with a final thought to chew on. If a simple table structure can literally create errors out of thin air, what hidden assumptions and future disasters might be lurking in your own spreadsheets and databases right now?